Ever wondered what the grid actually is, or how electricity gets from wind turbines out at sea, or even nuclear plants, all the way in France, to your home and onto your devices? Let's dive in and talk about each step of the process, all the general theory and maths behind it. To explain the grid, I've split this video into two parts. This one is the theory behind our electrical grid, an abstract of how it all works and why, and the second part, a deep dive into the history of the UK national grid, how it developed over the past 100 plus years and where it's heading. So let's talk about the physical stuff first. When we think of the national grid, the first thing that comes to mind is pylons. Giant lattice towers with cables strung between them. Static, near silent, and transporting something invisible we rely on for our everyday lives. But it's so much more than that. And I've put cables in quotation marks here because it's what most people say, but in fact a cable is only a cable when it's insulated, and we call them wires between the towers a conductor or a line, because they're usually not insulated at high or extra high voltages, and in the UK the pylons are actually called towers, but more on voltage and power in a minute. But for now, an electrical grid in simple terms is a power network that connects generators like our power stations, wind farms and solar farms to consumers in an efficient way, taking power from where it's made to where it's needed through cables and overhead lines. Along this path it passes through substations, which have a lot of functions but generally contain transformers, which raise the voltage of the electricity to make it more efficient to transport down our lines and cables, or lower it to make it more useful again near its final destination, like you, the consumer. Substations contain switchgear, like circuit breakers and disconnectors, which let us reconfigure the network and send power down different lines or break the circuit when a fault is detected. And earth switches, which make the system safe to work on and remove trapped charge from the system. And a final component, which is control and protection, which allows us to remotely monitor the network, control the switchgear and automatically protect it in a variety of fault conditions, like overcurrent when current gets too high, overvoltage when voltage gets too high, for example from a lightning strike, earth fault like when something touches an overhead line like a tree, or rock off like I described in my previous video here on blackouts, as well as a host of other amazing technical functions like distance protection and DAR, which I'll explore more in a dedicated video. So we just mentioned voltage, but what actually is voltage? Well, voltage, or electrical potential difference, is measured in volts and represents the difference in electrical potential between 2 points. In simple terms, you can think of it like water pressure in a hose. More volts means more pressure, so the water wants to go through the hose faster. A higher potential difference between 2 points means the voltage wants to get to that point more, and will flow the most through the path of least resistance, but will take all paths to equalise. Therefore, a low voltage is like low water pressure. That lower potential difference makes the electricity less eager to move. If you think about a low voltage battery, you can safely touch the positive and negative ends and you'll not get a shock, because the voltage is too low to overcome the resistance of your body to get to earth. The second part of the puzzle is current, measured in amps, and this is the second most important measurement when talking about electrical energy, and a key part of Ohm's law, and is crucial to understanding why the grid is built the way it is. Using our hose analogy, current is actual flow of water in the hose, or flow of electrons in our case, from one point to another. The final part of Ohm's law is resistance, and is the opposition to the flow of current, or in our hose analogy, a narrowing or obstruction in the hose. A low resistance means power flows more freely, and the lowest resistance materials are known as superconductors, whereas high resistance materials are usually known as non-conductive or insulators. Air is actually a natural insulator, which is why we use it in substations to keep our switchgear at a safe distance. However, extreme voltages can make even non-conductive materials into conductors, which is known as dielectric breakdown. The Ohm's law triangle is a great way of easily calculating for an unknown value based on two known values. Just cover up the thing you want to find and you're left with an equation for the two things you do know. And that's all you need to know about Ohm's law for now. We'll build on it as we move on to power. Power, measured in watts, is the current multiplied by your voltage. So higher voltage or higher current gives you more power. And here's another triangle, where you can work out any missing value from two known values. The graphs shown on screen are the relationship between current and voltage in Ohm's law on the left, where they are directly proportional, and on the right, the relationship when talking about power, where current is inversely proportional to the voltage, which is the basis of why we use high voltage power transmission. When people talk about the grid, they usually refer to voltage levels. In the UK, these are generally 11, 33, 66, 132, 275 and 400 kV. That K means 1000, so 400,000 volts, compared to the 230 volts in our homes. Voltage is something we control with transformers. Increasing the voltage lowers the current for the same amount of power, and that's a big deal. Let's look at an example. A typical 400 kV transmission circuit in the UK uses 3 phases, and each phase can have up to 4 conductors in an overhead line, given a total capacity of around 3.6 gigawatts. And since each tower carries usually 2 circuits, that's over 7 gigawatts of power on a single tower. Now let's talk about why high current, not voltage, becomes the limiting factor for cables. So you might have heard that higher voltages are more efficient at transporting large amounts of electricity, or that certain cables aren't thick enough for high levels of current, such as in your home. Both of these are correct, and in the simplest terms, higher current requires thicker conductors, which are heavier and more costly, and so are less desirable. A key factor on why more current means thicker conductors is Joule's heating, or I²R losses, which state that the power lost due to the resistance in the transmission lines is proportional to the square of the current I multiplied by the resistance R of the conductors. Therefore, P equals I²R. This means that even a small increase in current can lead to a significant increase in power loss. It's also why high resistance joints and poor connections heat up. Other factors why we don't like high currents include thermal stress, insulation degradation due to heat, producing excessive electromagnetic interference at high currents, cooling requirements and fault currents, which we'll talk about a bit later. So why does this all affect cables especially? Well, cables are often buried underground, in thick layers of insulation and armouring around their conductors. This insulation is essential for safety, but it also traps heat, reducing how well the cable can cool down. And that's why we perform detailed thermal analysis when designing cable routes to ensure the surrounding materials like soil, ducts or thermal backfill can absorb and carry away heat. But here's where it gets dangerous. Once the cable starts to overheat, the electrical resistance of the conductor, typically copper or aluminium, will increase. This causes even more heat to be generated through Joule's heating, and that extra heat further increases the resistance, and the cycle repeats. This is called thermal runaway, a feedback loop where temperature and resistance spiral upwards, potentially leading to insulation failure, cable damage or even fires. This is one of the key reasons why we avoid running high currents in cables wherever possible. And there are other drawbacks and physics behind why cables are generally inferior to overhead lines, except in specific use cases, which I'll cover more in my next video, but for now it's important to know that cables have practical limits. They're more costly over their lifetime, they have stricter limits on current and voltage, their ampacity or current carrying capacity depends heavily on surrounding thermal conditions. While overhead lines at 400 kV can carry 3.6 gigawatts per circuit, a 400 kV underground cable typically carries only 1 to 1.5 gigawatts per circuit, and that's with ideal soil conditions. In hot or constrained areas it can drop below 1 gigawatt, but with forced water cooling you can push that up to around 2 gigawatts, but that becomes expensive and complex. High voltage direct current, or HVDC, is another cable technology that's all the rage right now. It bypasses some of the limitations of AC cable systems, like capacitive charging currents, that restrict cable length, and is more efficient for long distances. A HVDC cable can carry around 700 megawatts per pole, and systems like Viking Link, which connect the UK to Denmark, can transmit up to 1.4 gigawatts over an incredible 765 kilometres or 475 miles. Therefore, we're incentivised to keep the current down, and we do that by increasing the voltage using transformers. It also helps explain why we use three-phase power transmission instead of single-phase, like you typically find in your home. If you're keen to dive deeper into these technologies and the physics behind them, hit that subscribe button to support the channel, and let me know in the comments what you'd like to see next. Power factor. So we've covered a lot on the basics now, including Ohm's law, calculating power in watts, and even looked at three-phase power. We can go a step further now and talk about real, reactive and apparent power and power factor. This is often one of the harder concepts in electrical engineering to understand, and in the UK is generally a higher education level of understanding, but let's break it down. Let's use the usual analogy of a pint of beer. Real power, P, is the power in watts that we're familiar with. This is what's useful and converted into actual work done, like lighting a bulb or turning a motor. This is the beer, or real ale if you prefer. Reactive power, Q, which is measured in volt amperes reactive, or VAR, doesn't perform any real work but is necessary for making inductive loads associated with magnetic and electric fields like motors to work, as well as capacitive loads. This reactive power oscillates back and forth between the source and the load. This is the foam on your top of a beer, a necessary part of the process but not as useful as beer. An apparent power, S, is the total content of the glass, both the beer and the foam. It's measured in volt amperes, or VA, and it's the combination of real power and reactive power, the total power supplied by the source. It's the total capacity of a system to deliver both real and reactive power. This can be expressed as the formula S squared equals P squared plus Q squared. Power factor is the ratio of real power to apparent power. PF equals P over S, and it can also be thought of as the cosine of the angle between voltage and current in AC circuits. As we've mentioned, some applications are naturally more reactive, such as motors, which are very common in industry. These industrial customers are therefore bringing the efficiency of the network down, requiring the grid to facilitate the transfer of large amounts of reactive power back and forth, without any real power actually being used. This transfer back and forth leads to losses on the transmission and distribution network, which must be accounted for, which is why industrial customers are charged for the apparent power they use, and may be penalised for having a bad power factor. This is in contrast to domestic customers, who are only charged for the real power they use. Let's take a look at the different types of power plotted on a sine wave. The sine wave you can see here shows the voltage plotted in a dashed blue line. The solid orange line is our current, and when both lines are perfectly overlapped, this is known as in phase. When the current sine wave starts to change earlier in time than the voltage, this is known as leading current, and is common in circuits with capacitive loads. Whether that's a capacitor or just a long underground cable, the system stores energy in an electric field. When the voltage across it starts to change, the electric field reacts quickly and current flows immediately. So the current actually peaks before the voltage does, and that's why we say current leads voltage in capacitive circuits. Think of it like anticipation. The electric field in a capacitive circuit gets excited before the voltage builds fully, so the current races ahead. When the current sine wave starts after the voltage, that's called lagging current, and it's common in inductive loads, like motors, transformers, and anything with coils. In these circuits, current doesn't flow instantly. Instead, the changing voltage creates a changing magnetic field, and that field induces a voltage, called back EMF, that resists the change. So the current takes a moment to catch up to the voltage, and that's why it lags. So why does it all matter? Well, let's bring this back to power factor. If a system has lots of inductive loads, like large motors, the current lags behind the voltage, which drags down the power factor. To fix this, we add leading reactive power, the kind produced by capacitive devices, to pull the current phase closer to the voltage. The simplest way to do that is by installing capacitor banks, which cancel out some of the lagging reactive power and help improve the overall efficiency of the system. You'll often find mechanically switched capacitor banks or MSCs in substations and smaller capacitors on distribution networks in order to add capacitance to the network during times of high inductive loads and to help balance the power factor caused by renewables. There are other solutions for improving power factor, such as synchronous condensers and certain types of harmonic filters, but we'll explore them in depth another time. Before we move on, there's another crucial measurement on the grid we need to explore, which is frequency. Frequency in its basic sense is measured in Hertz, and when we look at a sine wave is literally the frequency at which full oscillations occur each second. A full oscillation for an AC waveform is when it crosses the x-axis once in both directions, as shown here. When we look at the power grid as a whole, frequency is actually the relationship between the supply of electricity and the demand for it, or generation versus load. When we talk about grid stability, this is usually what we mean, and there's actually a section on grid code compliance that states the tolerance for frequency. In Europe, Asia and parts of Africa, the frequency is 50 Hz, and in North America and parts of South America, it's 60 Hz. We'll explore why in another video, but electronic devices are built on this known frequency, so it's important to keep it as stable and close to this as possible to not damage them. We can run into under-frequency situations when supply is less than demand, or put plainly, there's more load than generation can supply. Therefore, more power is being consumed than generated. Over-frequency occurs when supply exceeds demand, or more power is generated than consumed. The grid mustn't deviate from its standard frequency, as this can cause equipment damage, reduced efficiency, or blackouts. In grid-connected equipment like generators, motors and transformers rely on synchronization with the grid. If you want to know more about what we do when we have a blackout, check out my video up here. Frequency is closely monitored at the network control center, so that frequency can be controlled either by using up excess energy on energy storage, providing energy at a reduced price to higher load customers to encourage them to use it, or selling it via interconnectors. Similarly, they can turn up or turn down generation to push frequency in the other direction. There's many different ways to control the frequency on the network. Generation. For now, it's important to know that historically we've generated most of our electricity by spinning large steam turbines, powered ultimately by burning coal and gas, non-renewable energy sources. These generators were able to produce lots of reactive and real power. However, now that we've moved to predominantly renewable power sources, these come with their own challenges regarding reactive power and balancing the grid. For example, solar panels produce direct current, which must be inverted to alternating current to be put on the grid. These inverters produce only real power and traditionally no reactive power, meaning they couldn't support reactive loads on the network. However, modern smart inverters are much more capable. They can both inject and absorb reactive power, which allows them to contribute to voltage regulation and power factor correction at a local level. These functions, often called Volt VAR support, are now commonly built into solar inverter firmware and play an increasingly important role in maintaining grid stability as renewable penetration increases. Some smart inverters can even operate in grid forming mode, which allows them to provide voltage and frequency reference, but that's something I covered in my blackout video, so check that out if you want to go deeper. A major contributor to the UK energy mix is wind generation. On some days in 2024, wind had provided over 40% of the UK's electricity demand, and wind turbines come in different electrical configurations. Direct drive turbines use synchronous generators with permanent magnets, and these are electrically simple but mechanically more complex. More commonly, large onshore and offshore turbines use doubly fed induction generators, or DFIGs, which have power electronics that allow independent control of both active and reactive power. DFIGs are especially valuable because they can provide reactive support, helping to stabilise voltage, something older renewable setups couldn't do. While wind is more grid friendly than solar from a reactive power standpoint, it still presents challenges due to the intermittency and the need for balancing and reserve services, especially on calm days. So far we've covered voltage, current, resistance, Ohm's law, real, reactive and apparent power, power factor, as well as briefly covering the UK's energy generation mix. Now let's have a brief look at the actual electrical grid, what assets make it up and how this all matters. Now for a whistle-stop tour on how the grid works. At the start we touched upon generators, overhead lines and substations. Let's take a closer look. Our generators are where it all begins. Historically this was through burning coal, gas and oil. This was until 1956 when the first nuclear power plant came online at Calder Hall. The principle of all these power plants is the same. You generate heat either by burning something or through radioactive decay, in the case of nuclear fission. The heat boils water to produce steam, and that steam is fed through a turbine, causing it to spin, in turn rotating a generator to produce alternating current electricity. The generators produce power between 11 and 33 kV, so in industry we usually average it in say 25 kV. This power leaves the power station and then visits its first stop, a transformer, usually located in the power station and owned by them. This steps up the voltage to transmission levels at 132, 275 or 400 kV, ready to be transported large distances to where it's needed on overhead lines or cables. As we discussed earlier, stepping up the voltage for more efficient transfer. The power then arrives at another substation where it comes down off the overhead lines onto bus bars in the substation. It can then go through another transformer which steps down the voltage to a more manageable level for local distribution. This is usually at a Distribution Network Operator Substation, or DNO for short. At the time of writing in 2024, there are 6 DNOs which hold the 14 distribution licenses in the UK, which were previously the Regional Electricity Boards. If you'd like to learn more about the history of the grid, check out our next video on History of the National Grid. For now, this map shows the different licence areas and the respective DNO groups. The DNOs break each area down further, but for brevity I'll list the overall group. These are 10, 12 and 19 operated by UK Power Networks or UKPN, which is London, the South East and East Anglia areas. 11, 14, 21 and 22 are National Grid Electricity Distribution or NGED, which was formerly WPD or Western Power Distribution, and covers the Midlands, South Wales and South West. 15 and 23 are Northern Power Grid and covers Yorkshire and the North East of England. 16 is Electricity North West and covers the North West of England. 13 and 18 is SP Energy Networks or SPEN, or Scottish Power Energy Networks, and covers North Wales, Merseyside, Cheshire and the south of Scotland. 17 and 20 are Scottish and Southern Energy Networks or SSEN and covers the north of Scotland and southern England. The distribution networks operate at voltages up to 132 kV to move electricity around your local area to its final destination. The electricity will eventually pass through its final transformer, sometimes called a secondary transformer, where it can be taken down to 400 volts 3-phase to supply 3-phase customers such as small industry, farms and larger buildings. Or with the beauty of 3-phase AC power, each single phase actually supplies 230 volts individually. So each individual phase can supply a different circuit of residential customers at 230 volts. This is because if we divide our 400 volts total by the square root of 3, we get 230 volts per phase. This is because 3-phase power systems, there's 2 types of voltage to consider, which are line voltage, VL, which is the voltage between any 2 of the 3 phases, and phase voltage, VP, which is the voltage between any one phase and the neutral point. The relationship between these 2 voltages in a balanced 3-phase system form an equilateral triangle, with phases equal magnitude but 120 degrees apart. We can use vector analysis to show that line voltage, VL, is root 3 times the phase voltage, VP. From the diagram on screen, you can see when we draw that line between any 2 of the phase voltages, we form a triangle, with that line we drew being the line voltage. This applies to star-Y connected systems, which are common in distribution. A final point I'll leave you with that we briefly mentioned earlier is fault levels or fault current, which is the extra flow of electrical energy during a fault. In a normal power system, generators provide power to consumers, which act as a resistive load, or resistance on the network, pushing back against the generators. When there's a short circuit or fault on the network, the resistance provided by customers is bypassed, and the generators have nothing to push against, releasing more electricity than they usually do, which could be devastating to network assets. Fault levels can be an order of magnitude higher than normal current, and the network can't take this for more than a few seconds, so it's important we disconnect the short circuit as fast as possible by using circuit breakers. Circuit breakers have a limit to the fault current they can break, and if this is exceeded, they may fail to break the circuit and instead catastrophically fail. Rearranging the network and adding more generators often increases fault level, so it's important to consider. We've covered most of the basics of power theory now, as well as how transmission and distribution generally work. I'll save switchgear, protection and more for another video to give them the full detail they deserve. Thanks for watching, remember to subscribe for more electrical content and to catch my next videos on grid history, transmission technology deep dives and cyber attack vulnerabilities. The next videos I'm working on are the North Hyde Heathrow fire report, which is due to be published this month, as well as a video on the British steel industry among many others. If you want to support me directly and help decide what I put out next, consider joining my Patreon down in the description, like Benedict, so I can put more money into producing better videos. Thanks for watching, take care.